Okay, and I presume that my screen is visible also, and I will start the meeting now. I will start the lecture session for today. Okay, so we looked at several properties of this correlation matrix, which we said is Hermitian matrix. And I will be giving you a lab assignment on experimenting with these properties and confirming yourself that all the math that we went over last time actually is uh, observed even in the practice, in the practical experiments that you will do as a part of this lab. Okay, so what I want to try and do today is to look at the structure of this correlation matrix itself, specifically this correlation matrix RSS, and also this correlation matrix RXS. Uh, and we know that they both are related by this equation. RXS is equal to W RSS, W Hermitian, plus this identity matrix scaled by the variance of the limits. So I want to take a look at what is going on there for the specific case of the signal from multiple sources that we have considered in the previous lecture. So towards that, let us just do a quick recap that we have used or we have assumed that at the receiver, what we are getting at the input to our receiver, at the input to our FIR filter, is actually the input to our receiver is a summation of capital K different transmitters. They can be different simultaneously active subscribers to a particular communication system. They could also be, let us say, in case of cognitive radios, they can be total of K different what are known as primary users. Those primary users have the license to use the spectrum. And there may be some total of capital K such primary users active at any given time. They may not all be subscribed to the same system. They may have different subscription services, but the point is that over a particular spectrum or a particular frequency range that we are considering, there are a total of capital K different simultaneously active transmitters that we are denoting by x n of k. Remember, n is our time index, and small k denotes the index of the transmitter. And we are modeling this signal from the kth transmitter to have some modulation, amplitude modulation denoted by A of k, phase modulation denoted by this phase P of k. And we are getting that signal through electromagnetic medium, and so it is oscillating at some frequency f of k. This is known as the complex envelope notation of the modulated signal. And we have studied this as a part of CT516. Okay, now if you recall from the previous lecture, we collected this x of n's of k's for different transmitters, and we put them in a vector. And this we have called as our source vector S, or even a symbol vector S. And so that vector S is what I have formulated over here. It is nothing but all of these expressions lumped up together as a vector. Right? So It's just the received sample from different transmitters at nth time index. That is what we have done here. That is the definition of our vector S. Now remember, the purpose today is to evaluate this correlation matrix, the structure of the correlation matrix. And whenever we talk about correlation matrix, the underlying assumption is that these variables are random, they are statistical. And so for the time being, let us just assume, and this is the primary assumption that we will need to make at this time, which is that only these phases are random. I mean, in reality, even these A's are random also, F's are random also. But let us see how far we can go along by assuming that these phases uh, are all random across different transmitters. And this is a realistic assumption. This phase is actually a radio frequency phase. It is it is the transmitted symbol phase after it undergoes the radio frequency propagation medium. So there is no reason to suppose that the phase that we are getting from particular user is somehow correlated with the phase of the other signal. So this is a valid assumption that all of these phases are first of all uniformly distributed after they undergo the RF medium, uniformly distributed over 0 to 360 degrees, and they do not have correlation among themselves. Okay, there's one thing that is different here in equation 1 compared to the same equation that we had listed earlier. Can anyone tell me quickly? There's one change that I made here. Can you tell me what is it? Anyone? Okay, so the one change that I made compared to our previous formulation that I think you all have the slides now, we can go back and see. In the previous formulation, you will see that this A's of K's and phases P of K additionally had the index N as well. So previously, both the amplitude and the phases were dependent on the index N. Here, for the sake of simplicity, I have removed that dependence. The earlier formulation was more general, but here, this is one very specific assumption that I am making, and this is sometimes called the narrowband assumption. All that it means is that the signal is kind of narrowband. It almost looks like this exponential function, complex exponential signal, which, as we know, is the narrowest band ever. It is just one frequency f of k, right? Nothing can be narrower than just a single frequency. It is simply localized in the frequency domain. Now, if I remove the dependence of A's and P's on the index n, then they just become scalars. They become complex scalars. They don't change the nature of this complex exponential. If I plot the in phase and the quadrature component, they still are sinusoidal in waveform. It's only that their amplitude gets scaled by some constant A of k. Remember, A of k is now not dependent on n. The same way, phase also gets offset. But that doesn't change the actual waveform as it varies over index n. So in the previous lab, you would have simulated this exponential function, complex exponential function, and if you add this A's of k's and p's of k, it will look still the same, more or less, except you may feel that its amplitude has changed or its starting phase has changed. So when I remove the dependence of A's and P's on n, then I still retain the extreme narrowband nature of this signal. In the more general formulation that we had looked at earlier, these A's and P's were dependent on the sample index n as well. Now you can imagine that if I start multiplying each sample of this complex exponential, the sines and cosines, with different values of A's and P's every sample. That is what was happening in our previous formulation. If I have A dependent on not only K but index n also, and same with phase. Then and furthermore, if I assume that these phases especially are random, then it is easy to see that the waveform doesn't look like sinusoid anymore, because each sample I'm randomly just messing it up. I do take the complex sinusoid as one input, but then I just change the phase of it and the amplitude of it going from one sample to the next. And so therefore now, if I do have the dependence on n, then this entire term doesn't look like a sinusoidal waveform, meaning that it acquires a greater span in the frequency domain. It becomes a wideband signal. Typically, in the communication systems, this narrowband assumption applies because this amplitude and the phase don't really change on a sample by sample basis. If I have a transmitted symbol, that symbol lasts for many different cycles of this f of k. And so this narrowband assumption is not a completely invalid assumption, at least over a small period of time, over a small values of or a small range of variation in n. If I make n to be very large, I mean, if I change n from 0 to some very large number, then yes, if I'm collecting a lot of samples, instead of collecting maybe 50 or 100 samples, if I start collecting 1,000 or 10,000 samples, then obviously A's and phase will exhibit variation. But if I am looking at only 10 to 15 samples, then this narrowband assumption applies. So we are going to move along with this, what is known as this narrowband assumption. Okay. So because we have assumed that these phases are IID random, uniformly distributed over 0 to 360 degrees, then I can say that the expected value of the phase for one user that I have indexed by Q and another user that I have indexed by B. Remember, the phases are indexed by the index of the user, index of the transmitter. So I'm saying that if I have two different transmitters, one has an index of Q, other has an index of B, if I take expected value of the product of their phases after I take the second user and do complex conjugation, then first of all, because these phases are uncorrelated, this expected value just simplifies to the product of the individual expectations. And then what I can say is that the result is going to be 1 if actually I'm looking at the same user, meaning Q and B are the same. If Q and B are different, then I'm going to get a 0. So this is just a mathematical way of saying that the phases are random. The implication of the phases for different users being uncorrelated and random gives us this identity. Basically, this expectation is 1 whenever we are considering the same user, otherwise it is 0. And here what we have done is we have taken this expectation here, expected value of exponential of j phi q, and we have spelled it out how it looks like. We know that to do expectation, we have to multiply the PDF with the actual function itself. That is what I did here. and then we have to integrate it over the range of the random variable, which is 0 to 360 degrees. But now this complex exponential function integrated over 0 to 360 degrees is actually 0, because both the cosine and the sine, if I integrate them over 0 to 2 pi, the answer becomes 0. So that is how I got this 0 here for q not equal to b. When q is equal to b, obviously what happens is, even here, I don't even have to go this part of side of the equality. This part here itself becomes 1. You can see that when q and b are the same, this product becomes constant 1. And expected value of a constant remains the same constant, and so that is how I got this one over here. Okay, so now with that as our main basis, what we can say is that if I take the correlation matrix of this vector S right now, then what I'm going to get is just a diagonal matrix. And the elements along the diagonal are nothing but those amplitude squared. Remember this A values. These are, by the way, not complex numbers. These are the magnitudes of this entire complex number. So these A's are real values, and so I don't need to take absolute value of A before squaring it. This is how the correlation matrix of S looks like. There's a diagonal matrix whose diagonal elements are A of k squared. How did I get this? The only thing that I needed to make use of is this equation over here. Okay. How can I show this? I mean, fine, this equation is correct. We can convince ourselves that this has to be the case. But then from that, how did I get here? Well, what you can do is take this S to S Hermitian transpose. So instead of being a tall vector, it becomes a horizontal flat vector. And then look at each element by element multiplication. When you do that, you will see that along the elements along the diagonal, every time you are multiplying this term here with its complex conjugate. And in the matter of doing that, this ends up happening. The first line of this equation takes hold, and you get 1 for this entire exp terms, the product of the exp terms. Both of these exponential terms reduce to just 1. And this a0 gets multiplied with itself, and so you get a0 squared. For any term which is not along the diagonal, you are essentially taking expected value of one of the terms with multiplied with some other term. And so you end up having this situation where q is the index of the row and b is the index of the column. And that is how you end up getting 0 along the non-diagonal entries of this S Hermitian expected value. So I've given you a sketch of how to get this diagonal matrix as RSS, but I'll ask you to do it yourself. Okay. So maybe later today, when I give a new lab assignment, maybe some initial part will be this type of analysis that will be useful for you to do it yourself. MATLAB experiments will come after that. But if you have understood what I just said, and I said that we can leverage this equation to show this, then hopefully this part should be straightforward for you to show. Okay. Remember, what we are interested now is to get a handle on this correlation matrix RxX, which is given by this bracketed term. So we are taking a stepwise approach. We have said that under certain assumption regarding the signal vector S, what RSS looks like. And that answer we have mentioned over here. Now let us take the next step and look at the matrix term W RSS W Hermitian. Now this matrix W we have formulated earlier like this. It's an n cross k matrix, and its columns, it has k columns, and all of these columns are these complex exponential vectors whose elements are oscillating at the frequency of transmission of the kth user. So this is how we have defined this matrix W earlier. And now this is what we need to figure out, what this looks like. So the way we will try to simplify this expression is to write it alternatively in this manner. Okay, this is product of three matrices, n cross k, this is k cross k, and this is k cross n. So there are three matrices here which we are multiplying. It can be shown, and this again is what I am going to ask you to do using this pencil and paper, is that this entire matrix product can be written like this. What are we doing here? We are taking each user at a time. We are taking the W vector for that user and multiplying it with its Hermitian transpose. Who can tell me what will be the dimensions of this W f of k n times W f of k n Hermitian? What will be the dimension of this term here?
So 1.
1 cross 1.
N cross n.
Yeah, so Naitik said n cross n, which is correct. Remember, this W is a vector, n cross 1 vector. We are essentially taking one column of this W matrix. And so it's a column vector, it's a tall vector. Its dimension is n cross 1. And so if I take n cross 1 multiplied by 1 cross n, I obviously get n cross n. And that makes sense. Remember, we said that this matrix product is n cross k, k cross k, and k cross n. So this entire matrix product has a dimension of n cross n. And this W Hermitian also has the same dimension. So it kind of lines up. Basically, we are collecting a bunch of this W Hermitian matrices, in fact, for each of the k users. We are scaling each of those n cross n matrices by the amplitude squared of that user, and then we are just adding them up. And the answer that we get is the same as doing this matrix multiply directly. Now, this also shouldn't be too hard for you to show. You just first multiply this column with this diagonal matrix, this column with this diagonal matrix, and so on. And then basically you are going to get an n cross k matrix, and that you multiply with this k cross n. And when you just do this on a piece of paper, you will actually realize that it ends up being just this. But still, it is good for you to convince yourself of this equation. By the way, here, if this RSS wasn't there, it was not present, then all that will happen is this A of k will disappear. And you will get W Hermitian as just the summation of this k column vector multiplied by their Hermitian transpose. So this is a general equation. It applies for any time when you do When you take some matrix and multiply with the complex Hermitian conjugate of that matrix, you are actually adding this type of column by column matrices for all of the capital K columns. So this is some general statement that applies to all the matrices, not only for this particular expression. Okay.
Sure. This was the similar expression that we had got for eigenvalue and eigenvector.
Yeah, that is correct. The similar expression we had also got for the Mercer's theorem that Naitik is pointing out.
Sir, in Mercer's
these
result,
W's
are we
are
getting
not.
or are we getting 1 cross 1 when we are doing, let's say, an Hermitian in Mercer's?
Joel, your audio is little faint. Maybe you have to speak louder.
Sir, am I audible now?
Barely.
Okay, sir. Sir, I wanted to ask, in Mercer's results, we are writing. Sir, are you able to hear me?
Yeah.
So in Mercer's result, we are writing Rxs as some Q Hermitian delta Q, and then we are writing that as summation of, let's say, small m to capital M, lambda m, am Hermitian. But there, this am Hermitian term has dimensions 1 cross 1, right, sir? Or is it m cross n?
No, here again it's the same thing, right? These A's are the column vectors.
Okay.
These are the eigenvectors.
M cross 1. Okay, yeah. Okay, sir.
Right. So thank you, Naitik. I think thanks for pointing it out. The mathematical identity is exactly equivalent. Once you do this, you will also appreciate that spectral theorem or Mercer's theorem. Okay. Fine. So what we have done is we have taken this matrix and simplified it to this particular form. Remember, the way we are able to do it is because we have assumed that this RSS can be written like this diagonal matrix. If this was not diagonal, then this wouldn't apply. Okay. Now this is the last and final step, is that given this particular structure of this WRSS W Hermitian, we can take this RXX and write it as this type of matrix. And here all that we are saying is that it's a Hermitian matrix. But more specifically, the entries along the diagonals are all the same. They are denoted as R0. And the first column is R0, R1, R2 up to R capital N minus 1. And it's Hermitian transpose equivalent. So this element is obviously going to be R1 conjugate. And then the next one will be R2 conjugate and so on. So basically it is symmetric around the diagonal. And what are these R values? Remember, there are a total of capital N R values. This matrix, this entire matrix is N cross N. So the part which I would like you to show is that if I take, see, remember this entire matrix is uniquely formulated by just its first row, R0, R1, R2, and Rn minus 1. This is the identifying mark of the matrix. All the other rows or the columns are just either one of these terms or the complex conjugate of those terms. So that sequence R0 to Rn minus 1, it is called the correlation sequence of the input. Okay, it's the correlation sequence of the input. This we are still not processing it through the filter yet. Remember that. Here I am still looking at just the input to the filter. That input to the filter, remember, is just one sample x of n. And the correlation of the input signal or input sequence in the discrete time case is defined as expected value of xn times x conjugate n minus l. This is the definition of the correlation function. And what we are saying is that here in this expression inside this bracket, there are two indices, n and l. The specific statement that we are making is that the answer of this expected value is independent of n. It doesn't matter what time index you are considering. The answer that you are going to get is going to be dependent only on L, the small l. And that is why the left-hand side is indexed only with the subscript L. What it means is, for example, when L is 0, if I do xn times xn conjugate and take expectation of that, that answer is not going to be dependent on what sample index I am considering. The answer is going to be identical, and that answer is this R0, and that answer is forming the diagonal of this matrix Rxx. Similarly, if I take any sample in the time domain x of n and then multiply by complex conjugate of a sample that is delayed with by just one sample. So if I do xn times xn conjugate of n minus 1, then again the answer that I'm going to get is going to be independent of index n. It is going to be R of 1, the second element. And that is forming the first off diagonal after the main diagonal, and so on. That is one statement that we are making. And the punchline is that this R of L's can be written like this. R of L is summation of k equal to 0 to capital K minus 1 of ak squared times exponential functions. But now see that these exponential functions are dependent on just this L index, not the n index. This L is what is known as the delay index. It is not the time index. It is how much we are delaying one sample with respect to the other before doing this expectation. And so R of L has this expression, which is what I am asking you to show. Now, few things I can say that let us plug in L equal to 0. Okay, meaning that I am just taking xn times xn conjugate expected value of that. Now you know that when I do that, I'm going to just get the variance of x of n. Equivalently, I'm going to get the power of the input signal. If I plug L equal to 0, this exponential function becomes 1. And so as R of 0, I'm going to get summation of ak squared plus sigma u squared. Here in this equation, I have multiplied sigma u squared with this delta function indexed by L, which is to say that only when L is equal to 0, then this sigma u square is present. Otherwise, the sigma u square is not there. Essentially, what we are saying is that R of 0 is summation of ak squared plus sigma u squared, which is kind of understandable because in this signal that we have considered to begin with, you see the power of this signal is going to be the power of the individual transmitters, which is contained in this A of k terms. And so if I take the total power, it is going to be summation of ak squared. By the way, there is a noise term here, which I think I have forgotten to add. But once I add that noise term, then the power of the noise also gets added to the total power of the signal. And so then that is how I can justify R of 0 taking this exposure. Okay. When L is not 0, then surprisingly, this ak squared gets multiplied by complex exponential function of each of this f of k with index L. So now how can you show this? Okay, well, the way to show this is to look at this equation here. By the way, this part here, sigma square u delta L, that is not difficult to kind of add on, because somewhere we should have said that, well, we didn't. I have to go all the way back here. Here we said that Rxx is this term plus sigma u square multiplied by this identity term. Means that this sigma u square adds only along the diagonal of this Rxx. And remember, the diagonal of this Rxx is this R0. And so that is why we are saying that this sigma u square adds only to R0 by means of this delta L. So this term is just an add-on term that comes because of the noise, and it comes because the noise is considered to be IID random. It's a white noise. So fine. So this term, I hope that you all should be able to kind of get your arms around pretty easily. What about this term? Well, that term is coming from WRSS W Hermitian. But that WRSS W Hermitian we have written like this. Now, all you have to show is that, I mean, you will see that there is a structural similarity between what I am writing here and the expression of R of L. So all you have to show is that these terms here end up being nothing but exponential of j2 pi fk of L. Alternatively, here there is no dependence on index n, time index n, which kind of makes sense because this W terms don't have any dependence on index n, if you remember that. These W vectors are independent of the time index n. Maybe we can quickly go and look at it. See here, in this x of n, this n is the time index. That time index we have taken as the index of the scalar term that is coming outside of this W terms. Inside the W term, the time index is not present. More fundamentally, this elements are the contents of the tab delay line memory, and that memory structure is remaining independent of index n. That is why how I'm able to pull out x of n outside of this vector. So this W vector has no dependence on index small n. it still has this index, which is just the index of this shift register. Each of these m values, small m values. But these small m values are the index of the shift register. They are not the time index. Okay, so this convolution formula already tells you that this W vectors that we have used to define this matrix W, remember, this W vectors don't have any dependence on small m. Okay, and therefore you will, by making use of this equation, which also you will have to first of all convince yourself of, you should be able to show that this equation holds. Okay, so now this is actually an interesting result, because what we have done is we have kind of characterized in a statistical manner our input signal when there is a randomness to it. And in that case, we can now apply, there's a theorem called Wiener-Kinshin theorem. What this theorem says is that if I take the Fourier transformation of this sequence, although this sequence is not dependent on the actual time n, index n, it is instead dependent on this delay index L. Remember, time and delay, they are not the same. They are kind of same, but they are not the same. There is a subtleness here that I think you have to kind of get your arms around. By the way, those of you who are working on this OTFS, orthogonal time frequency space, that you would know very well the difference between the time variable and the delay variable. So here we have made R to be not dependent on time, but it is still dependent on something that is like time. That is this delay variable L. And therefore, we can kind of take its Fourier transform. Typically, we take Fourier transform of a signal which is in time domain. Here, we are taking a Fourier transform of a signal which is not in the time domain, it is in the delay domain. But it turns out that when we take for a statistical sequence, if I take Fourier transform of this correlation sequence, which is a function of the delay, what I get is the power at the different frequencies. And now these are the real frequencies. These are not some delay frequencies or some strange notation like that. So that is the subtleness here that I think you'll have to get your arms around it. But if this R was not a statistical entity, if it was not ACS, if it was not autocorrelation sequence, if it was just some regular deterministic time domain signal, then this L would be the time domain index. It would be actually N. And then when I take the Fourier transformation, I'll get the Fourier transform as a function of frequency. For the statistical case, you can take the Fourier transformation, but you have to realize that you are taking Fourier transformation of a quantity which is indexed by the delay index. But then when you take the same Fourier transformation, you get what is known as this power spectral density, which is a function of the frequency f. And this is our normalized frequency, which is periodic, which goes from minus 0.5 to plus 0.5. But it is equivalent to that index n. So in frequency domain, we get something which is equivalent to index n, but for that, for the time domain, we have to use not n, but the delay variable L. Anyways, so this is the Wiener-Kinshin theorem. And according to that, if I do the Fourier transformation of this expression, all of these exponential functions, as you may know, if I take Fourier transform of an exponential function, it just becomes a delta function located at that particular frequency. This delta function gets located at 0. And so, this delta function, which is located at 0 in the L domain, delay domain, it spreads out over all the frequencies. So it becomes a constant. And this ak of squared, they just appear because they are here. So what I get when I take Fourier transformation of this is this power spectral density, which is having this particular formulation. The sigma u square is constant, it is independent of f. And there are k terms which are all dependent on f, except they are direct delta functions located at f equal to f of k. This f minus fk comes because of when I multiply this exponential, which is a function of f, with this exponential, which is a function of f of k. So if you are a little fuzzy about the table of Fourier transformation, you can just look at any textbook. It will tell you that the Fourier transformation of exponential at some frequency f of k is a delta function centered at f of k, which is written like this. So this is the power spectral density. Let us plot it out. This is how it looks like if I plot it. X-axis is frequency f, small f. It goes from minus 0.5 to 0.5. And at each of this f0, f1, all the way until fk minus 1, I get a spike. And that spike is because of this direct delta function. I also get a constant, which is called the noise flow, whose height is sigma u squared. So this pedestal that you see is coming from sigma u squared. And additionally, there is a variability in these impulses, and that variability is coming because of this ak squared terms. Okay? So what we have done is we have proven that the power spectral density of this particular signal, remember, because it's a statistical signal, it's a random signal with random phases and so on, I can't just take Fourier transform of it. The Fourier transform of a random sequence is not defined. Okay, this is something that you have to keep in mind. Just like if somebody asks you that what is the value of a random variable at any particular time index n, you say that you would say that it's a it's a meaningless question to ask, because a random variable cannot have a particular value at any particular time index n. If I have a coin and if I keep on tossing the coin, what I get are sequences of the outcomes of a particular random experiment. I cannot say ahead of time, or I cannot ask anybody ahead of time that in that random variable, in that sequence of random variable, what is going to be the value at time index n equal to 10? Basically, what is the value of 10th toss of the coin? People will say that we don't know. I mean, you have to do that 10th toss. Maybe sometimes it will be head, sometimes it will be tail. So the question itself is meaningless. The same way, if you take Fourier transform of a random sequence and say what is going to be the output of that Fourier transform, the answer is it's a meaningless question to ask. you can't determine the Fourier transform of a random sequence. But you can determine this R. This R you can determine. And that is what we did exactly here. The only assumption that we actually needed was to say that those phases are independent. This was actually the only assumption that we used. And with that assumption, we were able to derive R. So the random sequence itself is not known ahead of time, but R is known ahead of time. R is deterministic in some sense. And therefore, I can take its Fourier transformation. And when I do that, I get this plot. Now, this plot is actually intuitively satisfying. Remember, we said that we have made this narrowband assumption. Remember, that is the thing that we started out with. Meaning that each of the signal looks like an exponential function. And the location of the exponential is f of k. And that is what this power spectral density tells us, that there are k exponentials located at each of these f of k's. And furthermore, their heights are given by this ak of square. So this answer that we got is very much matching with the narrowband assumption that we started out with in terms of the source model. Okay, so I'm going to take a break now, and I'll come back in just a few minutes. But what I'm going to do is I'm going to put here on the screen a proof of Wiener-Kinshin theorem. Are you able to see this document? Are you able to see this document?
Yes, sir.
Okay. So this I just pulled it up from, I think this is Professor Bowman is, I forget which university in USA. Anyways, so I pulled it up from a simple web search. And this is the proof of the Wiener-Kinshin theorem. The notations are slightly different. What we have called small r of L, the small r of L, Professor Bowman calls it r of x of k. So small r became capital R and L become k. So the notations are slightly different. Power spectral density became S, capital S, which we have called as capital P. And instead of writing this exponential term as J2 pi FL, he is writing it as omega k. Omega is nothing but 2 pi f. So this equation here is identical to this equation here. Oh, the other difference is L goes from 0 to n, whereas in this formulation, L, which is k, goes from minus infinity to infinity. But what he has done is done this derivation for a general case. In our case, there is no point of doing this summation from minus infinity to infinity because R of L has been defined as of now only from 0 to n minus 1. Well, this I have to be a little careful. In reality, okay, in reality, so there is a for the second line, behold, I have to say for in reality this length the value of n has to be infinity. I mean, we can make use of the Fourier transformation tables, which is what I mentioned just now. If I take Fourier transformation of this exponential, I get this direct delta function. That is correct only when n goes to infinity. Actually, this limit that I have written here, they are wrong. I should actually use this limit. So I will make that correction in an updated version. But what I would like you to look at is this proof of Wiener-Kinshin theorem. That is over here. So just go over it line by line. It's not terribly difficult to appreciate. I'm going to put this document also in our Google Classroom, so you will have more time to look at it later on. But otherwise, this derivation is kind of straightforward. So please take a look at it while I take a quick break. Okay, I'm back. We have probably spent about 1 hour of our time. I'll probably take another 15 minutes or so, and then we'll conclude for today. Okay. So yes. This was actually. I can go from this first line here, where RL is specified like this. Only if I am making this capital N, which is the size of this W matrix, to be infinite. So what it boils down to is that I have to take longer and longer observations, because this complex exponential function doesn't stop at some finite value of L. This is a mathematical function. It starts from minus infinity, it goes on to plus infinity. And so I have to make my observation window also to be infinite in the length. And then if I do this Fourier transformation, then I get this expression over here with these impulses at the location of the frequencies. In reality, I will never have the infinite observation window. N will always be finite. And so that is where a lot of the problems are coming from that we are going to look at now. Okay. So remember that what we have done so far is obtain the ACS of this X variable. This X is the input. We can collect capital N samples of the input and feed it to a filter, but that doesn't change the fact that X is still an input. And all we have done is characterize what this correlation matrix of X would look like. But when we started out, we said that our interest is to see the output of this filter. This WF of N is now a filter oscillating at certain frequency F. And remember, in the deterministic case, we have seen that the output of the filter is going to be that sink shaped function, which hopefully you did as part of your lab. And so we are concerned with understanding what this output is going to be like. Again, when we assume this input to be a random signal, then it is not meaningful to ask what the output of the filter is going to be like, but instead we should look at the expectation of the absolute value of the output squared. And when we did that, we ended up getting this particular formulation. And in that formulation, this RXX was sitting in the middle. And all maybe past 2 hours or so of the lecture session that we have been looking at was just on this RXX only. Okay. So now I want to come back to the original topic which led us to RXX, which is this expected value of the magnitude squared of the output of this filter. What I'm going to claim is that this magnitude squared of the output of the filter actually provides an estimate of the PSD itself. Okay, I hope it is not, I'm not bombarding too many things at you. This filters, actually, what I'm saying by this claim is that this filters actually, especially when I take the expected value of their output squared, it is as if they are taking the Fourier transformation of the autocorrelation sequence of x of n. It seems surprising that this is doing that, but in fact, this part here, this equation that we had looked at several lectures back, if you go through individual terms of this matrix, this vector matrix vector product, then what you may find is that that is very much like this one here, the proof of Wiener-Kinshin theorem. I mean, one thing that you will have to do is to make capital N approach infinity, as we just talked about. But if you do that, then that is what happens. This simple looking equation to spell out the individual terms, and if you try to correlate that, you get those multi-line, that multi-line proof of Wiener-Kinshin theorem that Professor Baumann has written. The only exception is that capital N will have to be made infinity. Now remember that we said that the power spectral density looks like this. And so if I knew the power spectral density, I would be able to know what the frequencies of arrival are. Because I'll just go and look at where the individual impulses are located. That will right away give me the location of the individual frequencies. And so therefore, the frequency of arrival problem actually can be solved by measuring these filters, so the filter output. Remember, the power spectral density is a function of this small f. And so I cannot just use one f. If I am unlucky and if I end up choosing a value of f which is somewhere over here, all I'm going to see is just the noise power. And then if I move a little bit away, then again I'm going to measure the identical noise power, and then again the same identical noise power. So I'll think that wherever I'm looking there is signal present, but actually that is wrong. It's only noise that is present. So I cannot just use one or two or few frequencies. I will have to use a large number of such filters, all at different frequencies, and then somehow take those f values as being present, for which this expected value of yn square kind of sticks out, like how it is shown here in this diagram. Okay. Obviously, this is one way to do it. The other way to do it is you have the samples which are incoming, right? We are just looking at x of n now. You forget about the filters now. Okay, forget about y of n squared and all that. You just get the signal which are incoming, and using the signal, you compute the autocorrelation sequence. How would you compute autocorrelation sequence? The expression is given here. When you are computing the autocorrelation sequence using the incoming signal, you will have to replace this expectation by what? in practice, what will I have to, I mean, if I am actually dealing with a practical situation where I have samples of the signal that are coming in to my receiver, maybe FPGA or any processing unit. Or if I'm doing this in MATLAB, I will have some samples of this random signal. I cannot take expectation because this is a mathematical operation which requires PDFs and so on. How can I still compute this R of L? To replace this expectation by
average.
yes.
We can replace the expectation by the normal average function. We can take the average rather than taking the expectation.
Are you able to hear me first of all?
Yes, sir.
Because I got a message saying that there is some network problem. Is everybody online? Are you able to hear me?
Yes, sir.
Yes, sir.
Okay. So Arushi was saying correctly that in reality we will replace this expectation by an average operation. And that averaging we will do over capital N samples. Okay, we will do xn times xn minus L, and then do summation from n equal to 0 to n minus 1 with small n. Maybe I should write it down here. So this is what we would do in practice. One thing is that I will have to put X sign on it, because this is not the actual R of L. This is R of L estimated using n samples. So this is the estimate that we will get. And we can say that the limit value of n to infinity r at of n L is actually r of. Is this fine? Hello? Anudeep, does this make sense to you? Okay, fine. I'm assuming that the network is not an issue. Let us see who all are here right now. Arushi, Anudeep, Bhavesh is there, Bibin, Divya, Joel, Komal, Kishan, Nemishi, Nitik, Nidhi, Priyanjali, Radhika. Okay, so everybody is there. And I'm assuming that none of you are having the network problems because I am getting this message on my console that there is some network connectivity. But I'm going to plug along. Okay, so what I was trying to say here is that instead of coming up with this entire all this topic of FIR filters that we started out with and all of that, if our objective is only to solve this frequency of arrival problem, we could just compute the autocorrelation sequence using capital N samples of the incoming signal according to that formula that I had just written. And then we would take its Fourier transformation. And then according to the Wiener-Kinshin theorem, I will get the power spectral density. That could have been one way to do it. Which one would you think we should do? Should we do this or should we do this one using our filters? Anyone? Komal, what do you think? What would be a better? We are saying there are two alternatives. One is to solve the FOA problems by using this filter. And the other alternative is to just directly compute the autocorrelation sequence and then just take its Fourier transform. Which one is you think looks better to you, more attractive? Maybe let us say computationally more attractive.
Hello.
Yeah. Komal, go ahead.
Yes, sir. Sir, out of two, I think the second option that averaging will be more easy computationally.
Okay. The averaging based approach is easier to Komal. Okay, I'll take one more opinion. Kishan, what do you think? Kishan, are you there?
Sir, I also think like the average is better. No.
You think averaging is better, Kishan?
Yes, sir.
Okay. Well, Komal and Kishan, this was a trick question actually. Naitik, are you saying something?
No, sir.
Okay.
Sir, can I
So,
interrupt?
sorry, Arushi?
Sir, if we are saying that computing ACs using the second method, we have to
Arushi, can you speak louder? I can barely hear you.
Sir, am I audible now
Yeah,
clearly?
yeah. Yeah, this is better.
Okay. Sir, so in the second alternative, we are computing ACS using the average function, which you have described earlier. Sir, in that, but the second line which you wrote, that we have to take large number of samples. So, sir, won't
No, I'm saying let us say number of samples capital N is the same.
Okay.
That is why I use the same variable N. Capital N is the same in both the approaches.
Okay.
Okay. Any other thought, Arushi?
Sir, if capital N is same for both the cases, then computationally.
Sorry, I can't hear you again.
Sir, if capital N is we are considering same for both the cases, then computationally, the second method would be a much better option.
Okay. Second will be better. Anybody else wants to say something, or I should move on? Okay. Actually, as I was telling you, this was a trick question. In fact, both the answers are same. They are identical. That is that is what the very first bullet says actually. That when I take this expected value of yn square evaluated using these filters, it gives me power spectral density. Now I can either take power spectral density like this, or I can take ACS and take its Fourier transform. I'll still get the power spectral density. And both these power spectral densities are going to be identical because I'm saying that I'm using the same value of capital N in either of these two approaches. So this first bullet and the second bullet, they were saying something strong. Basically, they're saying that it doesn't matter whether you go the route of these filters or you go the route of ACS. You are doing exactly the same. Not only that you will get the same answer, but in terms of computation also, you are doing exactly the same thing. Seems hard to believe, but that is how it is. That is why I put that proof of Wiener-Kinshin theorem on the screen. Okay, maybe let me elaborate this a little bit more. I think Joel had pointed out earlier when we had started this topic is that this Wn of f, if I take f to be k divided by n, and k is an integer going from 0 to n minus 1, these filters are nothing but the columns of the Dft matrix. And so therefore, when I'm considering this second part of this alternative, taking the Fourier transform, that actually is what we are doing anyhow here by multiplying the tap delay line with this filter coefficients. I mean, obviously we can, instead of DFT, we can use FFT, but the math doesn't change. It still is ultimately the DFT operation. Okay, so in this manner, where we take the incoming signal and take its DFT, what we are doing essentially is computing the filter output y of n, and then obviously for the DFT, the output of the DFT will have to be averaged over capital N number of samples. But with that, we get the same answer. Essentially, the autocorrelation function is not explicitly computed in this method, but it kind of effect, I mean, it kind of implicitly gets computed. Other way to say that is that if I take this DFT and then I get this power spectral density by taking the magnitude squared of the DFT output, and now if I perform the inverse DFT operation, I will get the same SES that I would have computed using the formula that we were looking at. So effectively what we are doing in this method of power spectral density estimation is we are taking our input signal and we are passing it through what is known as a bank of filters. Remember, we said that we cannot use just one filter. We have to use different filters for different frequencies. And one way to do that is to use the Dft filters, which are at f equal to 0, f equal to 1 over n, f equal to 2 over n, all the way up to f equal to n minus 1 over n. And then look at what is coming out of the DFT output, which is our yn samples. And then we'll take the absolute value squared. If we don't do anything else, then it is as if we did expectation using just one sample. We can obviously further refine that estimate by averaging this yn squared over multiple samples. But if we don't do that, if we just do yn squared, that's it for one output of this DFT, then that is when we get this equivalence. Okay, so maybe just 10 more minutes. What is going on in this FFT based estimation of FOA? Well, this W of NF, they are meshed to the input signal X of n, the component of the input signal which is oscillating at frequency f. Remember that we have shown earlier that this filter, maybe I should just quickly go to that slide. This filter, the expression of the filter Wn of f, and X of n, which is whose incoming frequency is f naught. When f naught and f are the same, then these two vectors, they become identical. And a terminology for that is that they are matched to each other. Okay, so the advantage of this FFT based estimation of the frequency of arrival is that in case if one of these k users is transmitting at a frequency f which happens to be one of these frequencies, either 0 or 1 over n or 2 over n, one of the DFT frequencies, then the output of the filter will be optimal in some sense. In what sense it will be optimal? It will be optimal in the sense of Cauchy-Schwarz inequality. You can't get any output which is more stronger than the output that you got by using this filter. Essentially, when Wn of f is matched to the input signal frequency, the angle between the two vectors, the filter vector and the incoming signal vector, that angle becomes 0. That is the definition of matching. They both become identical vectors. And so the angle theta between those two vectors becomes 0. And when that angle theta becomes 0, according to Cauchy-Schwarz inequality, you get the highest value at the output of the filter. This A is our filter Wn of f. B is the vector corresponding to the incoming signal. and when the matching happens, you can't beat it. You are going to so now I have several questions for you. Maybe I won't wait for the answers as of now, but I would like you to think of this later today. One is that, yeah, fine, we said that if the incoming signal frequency takes one of these capital N values, then by Cauchy-Schwarz inequality, our method becomes optimal. But what if the frequency does not take one of this k divided by n values? What if, basically, what if the matching doesn't happen? What if the input signal is not identical to the frequency of the input signal is not matching with this one of these DFT frequencies, which are k divided by n. Remember, this k divided by n, when k is an integer, gives us a periodic signal. This is something that we had looked at the start of the topic. And so what if, what we are saying is in this second question is that what if our input signal frequency cannot be written as k divided by n? Or what if the input signal frequency is greater than 1? So this first question, I think you should be able to answer because you are you completed the corresponding lab. Even the second question also you should be able to answer, and the answer of this question relates to that sinc function that we have studied earlier. And then finally, the third question is what are the what if the input is not a single source but multiple source, and each of these frequencies are different multiples, different values between 0 to 1 or minus 0.5 to 0.5. Okay, so basically we cannot guarantee, actually some of the answers I am giving in this slide already, but maybe you will have to think a little bit further on this on your own. In general, we cannot guarantee that the signal frequency is going to be this nice ratio k divided by n, especially when capital N is small. If n is large, then yes, maybe. But when n is not very large, and what is very large versus small, all that is kind of subjective to some extent. But what we can say is that in general, this optimality because of the Cauchy-Schwarz inequality would not happen. And when that, in those scenarios, our filter, what will happen is, it will generate non-negligible power at its output, even when the actual frequency is not the frequency of the filter. And that is what we have seen by that sinc function. The sinc function is telling us the output of the filter when the filter is fed with some frequency which is different from the filter frequency. This is the plot that I am looking at. Here, this is delta of f and f naught. F naught is the incoming signal frequency, and f is the filter frequency. So let us say that incoming signal frequency is 0.05 away from the filter frequency. in that case, our filter will still register a pretty strong output. It's almost as good as if it was matched. Maybe just 10% reduction also, or 20% reduction. Remember, ideally we would like this sinc function to be looking like this. That sinc function should be like this nice impulse. But instead of that, we get ripples. And it is those ripples which are problematic. When there is a lot of noise because of the ripples, a wrong filter can actually end up generating more power than the right filter. It's just the noise which will boost up the power of the wrong filter, especially when the frequency is close by. And this problem is even more amplified when we consider this multiple source problem, because now what will happen is that the output of different filters actually may fuse. They may just merge into each other. So this is what we will now very quickly look at, and then we will end after this. There are several issues, and all of these issues are happening because that sinc function is not the ideal delta function that we would like it to be. By the way, when will the sinc function start becoming like this ideal delta function? In order to make that sinc function look like this delta function, what we will have to do?
N should be large.
Yeah, n should become infinity. In reality, that luxury we almost never have. And so because of that, there will be several different types of problems which are all related because of the spreading that happens in the sinc function compared to the impulse. One problem is called smearing. Smearing happens when there are two frequencies, but they get fused by the main lobe of the sinc function. Okay, when there are two frequencies nearby, and I'm now considering the multiple source problem, what will happen is the output of the filters, because they are so close by now, they will kind of merge into something which is kind of like a blob. And this smearing happens because of the resolution problem. We can say that when we are considering a total of capital N samples, our resolution power, our ability to separate out two different frequencies is going to be inversely proportional to N. If the frequencies in this multi-source scenario, if they start becoming closer compared to 1 over n, then the smearing happens. And why am I saying 1 over n? The reason is because these frequencies are 1 over n apart. And remember, these are the ideal frequencies. These are the frequencies which are orthogonal. And the reason they are orthogonal is again because of the sinc shape. The sinc has a null at each multiple of 1 over n. That is what this plot shows. So if a separate frequency, another frequency is 1 over n apart from this one current frequency, then it is not a problem because it will sit nicely on the null of this sinc. But if the two frequencies start coming closer compared to 1 over n, then they will end up sitting on the main lobe of the sinc function. And that is where you lose the power of resolution. You won't be able to resolve those two frequencies. So you have a limited resolution once you fix on the value of n. There is another related problem which comes because of the side lobes of the sinc function. The smearing and the resolution relate to the main lobe of the sinc function. The leakage happens because of the side lobes. Basically, the sinc function leaks the power of this direct delta function. Ideally, the signal has this type of power spectral density. Okay, the actual signal has this type of power spectral density. It is very nicely localized, very thin impulse at each of the frequency. The problem is because we are considering a finite value of n, each of these impulses get replaced by this sinc function. And what is happening is that the power which is actually nicely concentrated at this specific frequency, it kind of leaks out everywhere. It's some type of splattering happens. And specifically, it leaks out into the side lobes. And that could be a problem if you have an actual weak signal which is present at the location of one of those side lobes. It will just get buried under the side lobe. You won't even know that there is a signal present. And then the fourth problem is the noise in the estimation itself. And that problem, as I think I briefly mentioned earlier, we can solve it by not just looking at the absolute value of this yn squared, but by averaging this yn squared also over multiple DFT windows. But if you don't do that, then that problem remains. So these are the four problems. I'm just going to briefly describe the smearing problem, okay, pictorially. So here I have used the same DFT-based method of estimating the frequency of arrival. I am assuming that there are only two signals which are present and their powers are identical. I am plotting this as a function of small f. So the unique range is only minus 0.5 to 0.5, but actually I am narrowing it down only up to minus 0.03 to some plus 0.06 or 7. I have one frequency which is present as at 0.01 and the other frequency which is present at 0.015. So the separation between these two frequencies is 0.005. And I am making capital N to be 500. Right? So inverse of 500 is 0.002, which is smaller than the separation between these two frequencies. The resolution power I have is good enough. And therefore the smearing doesn't happen. I can nicely see the two peaks. And I will say that my first frequency is at 0.01, the other frequency is at 0.015. I am able to solve the FOA problem. There is no issue here. Now, I use exactly the same input signal with capital K equal to 2, with F0 equal to 0.01 and F1 equal to 0.015. And I applied DFT on that, except that I said that my observation window is now not 500 samples, but it is 50 samples. Inverse of 50 is 0.02, not 0.002. 0.02 is bigger than the separation between these two frequencies. So my resolution power is now not good enough. Okay, I'm going to stop, Anudeep. This is the last slide. And so this is the result that I get. You can see that the two signals have smeared out. you can't tell that there are two signals present anymore. Everything has become one big blob. And so you can't solve the FOA problem any longer. Okay, so this is where I will end today's lecture.